Much earlier in the semester, I gave you the example of the Venturi meter, and I said that this was one of the ways that you could apply principles of material and energy balances in a useful way. In this case, it is figuring out what the volumetric flow rate is in a flowing stream. As I promised in that video, in this video, I will derive that equation that I showed you so long ago for the volumetric flow rate by applying the Bernoulli's equation to this system. So when I first introduced the Venturi meter, I just said that there was a pressure sensor at 2 points within the pipe, and that was because we hadn't talked about manometers yet. And a quick way that you could measure the pressure, or more specifically, the pressure drop between 2 points, is with a manometer. So this manometer fluid is in green, and it is measuring the pressure difference between the wide section of the pipe and the narrow section of a pipe. I suppose I should back up and just review again quickly what a Venturi meter is. A Venturi meter is the combination of a constriction in the pipe, so that's the middle section, that makes the fluid flow faster. And by measuring the pressure difference from the upstream part where the flow is wide and the choke point where the flow is narrow, you could then obtain what the volumetric flow rate is. I got a couple of really good questions and emails from students who asked, well, wouldn't the pressure in the middle actually be greater than the pressure upstream? This is a very common misconception that you'll cover in fluids. That you think that because the constriction of the flow makes the pressure greater because that somehow squeezes it. And that is incorrect, because remember that liquids are incompressible. So that's one of the assumptions that you have to make. For incompressible flow, P1 is going to be greater than P2. And that reflects the fact that fluids always flow from areas of high pressure to areas of low pressure. So if the reverse were true, if the pressure were actually higher in the constricted section of the pipe, the flow would actually be going backwards, because fluid always wants to flow from high to low pressure. So the way that this works is that it's not the pressure that's increased of this middle section, it's that the velocity is increased. So that's another item that I introduced far long ago, but didn't really talk about till later on in the semester. V dot, the volumetric flow rate, is equal to the velocity of the stream times the cross-sectional area. And if I have an incompressible fluid, remember that the volume is not going to be affected by the pressure, and therefore my mass flow rate is going to be the same if I have a steady state process. So if I have mass that's flowing into a certain section of the pipe, mass also must be leaving another section of the pipe at the same flow rate, or else I'll have accumulation within a pipe, which cannot really happen. So M1 has to be equal to M dot 2, the mass flow rate, by conservation of mass. By conservation of mass, M1 is equal to M2. I can express the mass flow rate as the density times the volumetric flow rate. So instead of M1 equals M2, I can write the density of the fluid at point 1 must equal the volumetric flow rate at point 1 must be equal to the density at point 2 times the volumetric flow rate at point 2. And what I just said is for an incompressible fluid, my density is going to be constant. Rho is not a function of pressure, is another way to think about it. And therefore, rho 1 must be equal to rho 2. And I can simplify this expression simply by saying V1 is equal to V2. Now I can write volumetric flow rate as the velocity times the area, and I can furthermore say U1 times A1 is equal to U2 A2. So this is going to be an important step in my derivation for later. So at this point, let's back up for a moment. So from this point, it's clear that you could measure the velocity of a fluid, and just simply by knowing what the area of the pipe is, you could then calculate what the volumetric flow rate is. But consider that you can't really measure what the velocity of a fluid flowing in a pipe is without some instrumentation. And that's where this pressure measurement device, the manometer, comes in. So you can combine these two ideas with the Bernoulli's equation in order to solve. So like I said, let's back up. Let's remember all the important parts that I got from this analysis But let's start now with the Bernoulli's equation instead. By looking at Bernoulli's equation, it's clear that I can relate the change in pressure, delta P is P1 minus P2, to the change in velocity, U1 minus U2. If my Venturi meter is mounted on a horizontal section of the pipe, there is no height change, and I can neglect the G delta Z term for this situation. And I can proceed from there. So let's walk through term by term. Delta P is going to be given by the manometer. Right, so here I have an H, and it's important to not confuse this H with the H from the potential energy. So this H is related to the manometer equation. So by manometer equation, or a manometer balance, remember this topic from all the way from chapter 3, right? I can say that P1, taking the pressure on the right-hand side, and I'm going to assume that the density of the manometer fluid is much denser than the flowing fluid. So I'll just make a quick note of that. Assume rho F is much, much greater than rho. Right, so P1 is on the left-hand side. On the right-hand side, I have P2 plus rho of the manometer fluid times GH. So therefore, delta P is equal to P1 minus P2 is equal to rho of the fluid times GH. So if I look at what the difference is in the two height levels of the manometer, I can simply plug that into my rho GH to obtain what my delta P is. So in my Bernoulli's equation, I can write that. Or I can just keep it as delta P. I'm going to keep it as delta P right now over rho. So importantly, rho is of the flowing fluid, and rho sub F is for the manometer fluid. So keep those two straight in your minds. Now, delta U squared I can write as the velocity at the second point squared minus the velocity at the first point squared over 2, and that is equal to 0. And as I explained previously, I can write the volumetric flow rate is U times the area, and therefore the velocity is equal to the volumetric flow rate divided by the area by algebraic rearrangement. So because I know that the volumetric flow rate is the same because it's an incompressible fluid, I can now write delta P over rho plus, and the V is going to be factored out. So V squared times 1 over A2 squared minus 1 over A1 squared, all over 2 is equal to 0. And now from here, I can rearrange this to solve for V dot. So I'm going to take the delta P over to the other side and then multiply through by 2. So I get volumetric flow rate squared times 1 over A2 squared minus 1 over A1 squared is equal to minus 2 delta P over rho. And then I can take this whole term over to the other side and take the square root. So V dot is equal to the square root of minus 2 delta P over rho times 1 over this term. Right, and this is not the same exact form of the equation. I think I did some more algebraic manipulation to the form that I had from before. But if I replace rho GH in for delta P here, rho FGH, now I have an equation that H is my only unknown, right? So I also have to know how large the constriction is of the pipe. I have to know what A2 and A1 are. And I also have to know what the density of the manometer fluid is and the density of the actual fluid, right? But if I know all those things, then that allows me to then have an equation that I can use to simply plug H in and find what the volumetric flow rate is. That will conclude this video. Once again, this is just an application of the Bernoulli's equation in a useful way in the Venturi meter to find what the volumetric flow rate is in a flowing stream by looking at a process variable that is easy to measure, which is the height of the manometer, which will change depending on what the pressure is.